You're live. See, there you go.
But it doesn't show anything.
I mean, there is a delay, so maybe. There it is. You're live.
That 20 minutes is fully roughed out in the back pocket, correct?
Yep. Yeah, roughed out, the pocket, and like one other feature. Like finished. Yeah, because we're I think we're like about 10 minutes on roughing. So yeah, and then that fucking pocket was 6 minutes. And then I had like a couple other features, just quick finishing them just to see what that would be. And that got us to like 17 and a half stuff, but then I bumped it up. Don't judge, bro.
Alright, Clay. Put the fucking link up.
Okay.
And somebody's gonna have to be there fucking vote for Facebook and stuff. Facebook thing.
Hey Eric,
What's up?
is your phone, is it fancy enough to do wide angle all the time for video?
Yeah.
Can we potentially borrow it? Oh wait, shit. Well, you can
Paul can do the Facebook on his phone.
Yeah,
I don't know how to do Facebook, bro.
I'll do it on your phone, man. We're gonna do it on Instagram and Facebook since we're already doing it.
So you go to
We're gonna throw it on Instagram.
hit the
You just want wide angle of his ass, like fucking like that
No,
or
we
something?
actually have cell phone things that hold it on the screen.
Hold the cell, what?
It holds the cell phone and it just points towards the screen.
I don't want to fucking record the goddamn. Oh, that's what it's for? Is to record the screen?
Yeah.
So
Get
yeah.
it onto Facebook or whatever? Or
You know,
Instagram?
everybody can hear you currently too, by the way. Just letting you know. It's on.
We're live.
Hello, everybody.
3 people are watching.
Obviously, our bleep machine's broken at the moment. Is anyone watching?
Yeah, 3.
Oh.
Because
Alright.
we're just gonna put it on Facebook and Instagram at the same time.
Right. Oh, you don't even have a webcam to like see you? That's
No.
kind of boring, dude.
I don't have that, bro.
Oh, you gotta get a webcam. That way you can be like the little dude in the corner. Like, hey, this is how this happens. I might be able to yank mine. Well, no, mine's all like zip tied onto my thing.
That would have to be yours. Yeah.
Okay, so
both
I
Eric
don't-
and Clay thought this was a good idea. So.
I don't have. How do you want to stream this on what, Instagram? I assume then, because I don't have
Yeah.
Facebook on here.
Yeah, I'm gonna have to do the Facebook.
Okay. I hope the Instagram
Dude,
will
now
work.
there's
The wide angle.
5 people watching.
Yo.
I'm one of
Oh,
them.
oh, okay. I was gonna say, and now there's 4. Someone was rude and just left.
Alright, it is on the Facebook post. Can't really do it on the Instagram one because they can't click it. But
We're definitely gonna have to keep the office doors closed. That machine's gonna be loud and nasty. Alright, so let us see here.
you can send me an email. You are now live on YouTube.
Did you put the link up?
Yep.
I guess if I go live, you can always just find that link and like post it up. So
Yeah.
I don't actually have to save that as a text file.
Yeah, I posted it on.
Did you make it the thing on Instagram?
I'm working on the
I can do that
Instagram
on
thing right now.
like live link. Yeah, I'll do that.
I'm working on doing the Instagram live right now too, but it doesn't look like I can do wide angle.
Whoa, does our,
On
like, look,
Instagram
the
Live.
thing has our logo on the bottom right hand screen. Clay, did you set that up?
On what?
Where our
Oh, is
logo's
that-
always
I
on
think that's your
the.
OBS studio?
It's
No.
like that in every one of our videos.
Really? It
Is that
just
just a-
automatically does it?
That's a
Yeah.
YouTube thing?
You have to upload your logo into it. And then
That's
it's on
pretty
there.
fucking.
Yeah, that's cool.
That's pretty slick.
Yeah. Cool. Who said something? Your volume is really low. Hey, you probably want to turn up mic volume or something.
I don't know how to do that. Well, it's also down there.
Oh, well, yeah. How's it now?
Can you hear better now? See if they answer.
Yeah.
We also don't know how much lag there is, so.
Yeah, dude.
Alright.
At least I would say at least.
I guess
10
we could
seconds.
probably start the live thing.
So Instagram Live does not let me do my wide angle lens.
What?
I mean, yeah, it doesn't allow me to pick lenses and stuff. while
Allow
on Instagram.
Facebook to record audio. Oh. Oh. I don't know about that.
You can undo that setting later though.
I guess. Yeah, I'm probably just gonna knock my phone off there. Okay, so volume is better.
Alright, the
Sweet.
link is on Instagram story and Facebook post.
No, I'm just waiting on Eric to get this Instagram.
I mean, I'll do it, but
You don't have
like
to
I
stand
said,
there though. We have a thing that
no,
holds it.
I know, I got
Where'd
one.
it get
I'm just trying to situate it. Hey, you're live. I'm just trying to situate it in a way that like makes sense. You want them to see the screen though?
Yeah, that's what they want.
That's what they want. Okay, so that screen. It's gonna be terrible.
I know. You're not changing my opinion.
Alright, I need to like, the mount is too lean back.
Hey, Tom's on. What's up, Tom?
I need to like prop this.
Plus,
forward.
remember my hand's gonna be coming right here.
God damn. Oh, sorry. Forgot we're live.
Yep, we are live.
Can't be saying profanities.
I don't know.
Alright, so,
But yeah, do you want to do this or a hard one?
I mean, your phone can only see like part of the screen.
Yeah,
correct?
no, that's why it's terrible.
Hardware
But
picture. You got the hardware
Alright,
picture?
well, I guess I'll just do part of the screen then too, on Instagrams.
maybe I can figure out how to do multiple streams on the thing. But that's why, if you're on here, if you want to see a better video, go to our YouTube. Our YouTube is an actual screen capture. So it's much better resolution. But you can't see, on YouTube you won't be able to see Clay as he walks by the computer screen though, so. But we have, alright, we have a few people live. We have 7 on YouTube, we have 14 on Facebook, and I don't know how many on Instagram.
15 so far.
15, cool, okay. And I will say it's close enough to 12:30 as it is 12:30 now. So we can go ahead and begin. So we haven't done one of these for a while. This is CFD Friday. We're currently going to work on showing the Supra kit that we have been working on. Some of the parts are done, some of the parts are not, some of the parts are in process. But we're going to show you the CFD process, answer any questions. We have a lot of questions from last week that I will go over and try to answer, which some people have questions on. Again, since there's more people on, if you want a better view of the screen, please go to YouTube, as it will be much better quality and you can see what's going on. It's just our page at Ferris Engineering. I think Clay also posted a link to it on our Instagram main page and on Facebook under the post. So, on that note, we shall begin. So, currently, I was talking about we are going to be looking at the Supra, thus Supra. So currently, we are looking at a CP plot of the Supra. CP plot is, whoops, apparently that screws that up. So, this CP plot. So I'm just going to show this as generically on the screen currently, and then I'm going to kind of go over the questions first, so when there's new questions, I'm not answering a ton of them at the end. So when the screen blanks out for a second, don't mind that. That is just me switching something on my other screen. One of the questions that was asked was CFD on Windows up and down. What is the difference? We've never actually done a test with the Windows down. There will be a difference in the results, but We can't tell you exactly what that is, and it would depend on how accurate you want it. You would need to fully model the interior or model the interior in somewhat of a way, and then we wouldn't know exactly how accurate things are depending on how accurate the inside is. Plus, you need to model up an actual human in there. There's a lot of things that go into it that we have not done. We also don't know if it's fully useful to do that. It is something we have talked about. We especially talked about it when we were working on the Miata with modeling it with the top down, but we never actually went that far with that car. Another question with different diffuser angles affect flow. We do have a blog on diffusers, but it's not specifically about the angles. There are a lot of effects on diffuser design, and this would kind of be difficult to show in this kind of presentation. We might look at doing something similar to that, maybe, if I can come up with a good creative way to do it, but I do not know how to do that. Another person asked if I would solve Navier-Stokes equations live. Not going to actually do that. That sounds really terrible. Yeah. And then another question by, I think it's the same guy, how did you iteratively run different cases to hone on to optimal configurations? That's kind of a little bit easier to answer. Basically, we decide on what outputs we want in the case that we're specifically running. So say we're talking about the Porsche. What are our goals with the Porsche? That's the big thing you need to go on when you're looking at honing for an optimal configuration, because optimal is in the eyes of the beholder. Like, somebody's optimal is not another person's optimal. So we have to have clear goals when we set out on setting everything up. So that is the first thing. You have clear goals, and then you need to know what data or images. When you're talking about CFD, you would look at data and images that you specifically need to look at so you know what's going on in the flow. Run baselines. Baseline tells you what your starting point is, and having accurate data is also good, so you know what your changes are doing, if they're having positive or negative effects. Make a change based on looking at the data, and then run it again. See if your changes actually helped. Sometimes they do, sometimes they don't. We'll run a ton of iterations, and sometimes what I think will make something better actually makes it worse, and I guess I wouldn't test it vice versa. But basically, some things that we test don't always work. So that's why we have to run it iteratively. And then another question was, what iterations do we actively go through? And then it's basically design CFD results. And then once we have the results, we have to look at those results, make a decision if that is good enough. If it's good enough, we go to production, and then go to the track. If it's not good enough, we go back to the design phase and go back through all of that. That's basically how the iterations we go through. Another question is, what solver and inputs do you rely on? How big are your meshes? How do we run our simulations? Do we run on the cloud, and what CFD program? So I'll go through. So the solver, we use the simple algorithm. It's basically an implicit method for pressure-linked equations. That's what simple stands for. It's basically a steady state, pressure-based. The inputs that we use is obviously the CAD, so the model that you're using, the design, the car, whatever you are looking at testing, we have that in CAD, which is computer-aided design. If you don't know, we use NX. I guess I'll say that since people ask what programs we use. You need to know your turbulence model you want to use based on the physics that are going to be applied, what kind of boundary conditions. Sometimes we'll run multiple reference frame for the tires or the wheels. Sometimes we won't. It really just depends on what we're looking for. Mesh, that's a really hard one. It really depends on what the model is, what we're doing, how complex the model is. It could be as small as 10 million cells to as large as 80 million cells. What velocity do we use for simulations? We're usually around 80 mile an hour. And CFD, it's always in meters per second, so we're always looking around 35.763 meters per second. Going through the questions. How do we measure data from the parts? So that's simple. And I can actually show you that on the screen too. That'll make it easy. So each of these components are a different part. And we can basically pull force and moment off each of those parts. So we're looking at the dive plane. So you can see the dive plane lower right here and upper. We pull data from the top one, the bottom one, on the right and the left side separately. And then we can look at the data. Usually they're fairly similar. I did run this in yaw, so there is a slight yaw in this, so the right and the left do see a little bit different of a load. The reason for that is because the airflow is almost never perfectly down the center line of the car, so applying a little bit of yaw, it's going to lower your numbers. It's going to make it more accurate to real world numbers you'll see on track. If you're going down the straight at a track, the airflow is never going straight down the car, so it's always going to be seen in yaw. So that's why we do that. That's how we do it. We basically, like I said, forces and moments. If you're curious about what the data looks like, somebody can ask on there, and I will go through on kind of like how we pull that data and how we calculate it. I think I have, basically we pull the data. It comes off as a .dat file. We run that into a CSV file, and then from there we run the CSV file through a Python script, and I output a text file that gives us forces in X, Y, and Z, and moments in X, Y, and Z. And the moments you use for aero balance, if you're curious. Then lift/wheel venting with louvers, the difference between styles and how the air is channeled underneath the car to reduce filling of the arches. That's kind of a complex thing to answer that would need to kind of go into an entire thing by itself, so I'm not going to really get into it, but I did read the question, and that's something that we'll put on the list. Simulations needed to obtain an aero map. In the process, you go about iterating changes on the aero parts you obtain. I guess for coming up with an aero map, that's pretty easy to answer. First, you need to know basically have an idea of the time that you're in cornering, time you're in braking, time you're at max speed, time you need traction. You need to know all those because that's different aspects of the car and how it's situated on track. So you need to know those times so you can make judgments on where it's important to focus on the aero map. Why you need an aero map, ride height sensitivity. Your aero loads change with your ride height, and the more sensitive it is, that's bad. Obviously, the more stable it is, you'll actually have more usable downforce. So that's why aero mapping is pretty important. So the more aero mapping you can do, the better. Weighing the difference of car conditions on track, where do you want to run the car, and basically you can do the runs to generate 3D maps, and I can actually show you an example of that. I saved a picture somewhere. There we go. Here's this. And then I think I put that in documents maybe. Nope. Here we go. So this is an example of like what aero maps look like, just for an example. So if you see something like this, so you can see we're looking at 4 different types of configurations. So you have front downforce, total, and then it changes with full screen it. All right, full screen. So this full screen. So we are looking at it. So front downforce on. So I'm at the top left graphic. So front downforce in pounds, and then we have ride height in the front, ride height in the rear, and you can see how that changes total downforce. So the color is your front downforce. Sorry, I said total downforce. I meant front downforce. So you can see how that changes. And then you may move over to the right to the rear downforce. So that changes. So you can see how the front ride height and the rear ride height changes the rear downforce, and then you can see total downforce. Same concept. You have the ride heights, and then the downforce. And obviously the rear is making more downforce than the front. You can tell by the numbers on the charts. And then drag based on the ride heights. Obviously, looking at the chart, drag is much less sensitive on the actual ride height map. This ride height map is also just a generic one. I pulled it from past information I have. It's from an open wheel car, but this is not the Supra. So if you think this is Supra, it's not. these numbers would be way too high for the Supra. But this is what an aero map looks like. Just because we had like 2 questions on aero map, so I thought I would kind of quickly go over like what it actually is. Now I gotta figure out how to leave full screen. I don't usually look at pictures on this machine, so. And then another question was LES or RANs. So people who don't know what LES or RANs is, not really a big deal, but we mainly run RANs, which is Reynolds Average Navier Stokes. It's regular. When you're usually talking about RANs, it's steady state. So the steady state is normally what we run. There's also on transient RANs, which is usually called URANs. But if we're not running steady state, I usually then run what's called IDDES, which is Improved Delayed Detached Eddy Simulations. So what it does is it treats some areas as unsteady RANs and others as LES. We use either the Spolar, I don't even know how to say, Alarmist, or K Omega SST turbulence models. And then the LES is basically large eddy simulations. The reason we don't run LES is it's just very intensive on computing resources, and we don't feel it's actually necessary for what we're trying to do. Another one is how front canards work in a couple of runs at different heights relative to the rotating wheels. So I can kind of go over how we do canards. We might do a case maybe where we do a few different heights for canards and how it changes stuff. Maybe I'll put that on a list of one of the next cars we develop. I'll make sure to add, because we do all these runs, but I don't always keep all of the data of the runs to pull up. I'll output images and data, but I don't keep it past that. So actually doing a CFD Friday on that, I'll have to basically set out to do that, and then I'll keep 2 runs of 2 different heights, and we can kind of go over the differences and what we're seeing then. But basically, how we design front canards might be different than how other people do it, but a lot of the goal with what we do for that is to create vortices off of them to help pull air out of the wheel well. They can be at a high angle of attack. Like a lot of times you see them, they're like a pretty high angle. Like you can see the ones on the Supra, they are on a pretty high angle overall. But the flow can stay attached to them because it is going around the bumper. Around the bumper has high velocity, low pressure around that, so it's going to stay attached more likely. So they don't actually create a whole lot of downforce themselves. They're mainly used for tuning aero balance, and then we use it to help evacuate air out of the wheel wells. I don't know if that's how everybody does it, but that's how we inherently do it. And then kind of another question is point out how air is managed and manipulated through key areas of the vehicle like wheel wells and splitters and underbodies. I'll kind of go over that once I start going over the CFD. Another question was explain how barge boards, turning vanes, and other devices work. That's going to be kind of hard on this CFD Friday, as this doesn't have any barge boards, turning vanes, or anything like that. This was specifically meant for like Formula One. Like what do those things do? Maybe there's a car that we have done barge boards on, so maybe when we do a CFD Friday on that one, I'll get with them on that car. Maybe we can kind of go over that then. Another question. These were the last 3 questions from today, from not the chat. I haven't gone through the chat questions yet, but asked about CFD on a 2-element wing. I'm not really sure what the question was on that, so if you can clarify, I'll go over that on another CFD Friday. Another question was specifically on the Supra diffuser angle defined by aero efficiency or exhaust clearance, and so I'll flip it over to the diffuser side so we can kind of see what's going on. So it's always both. So it's not defined only by aero efficiency or exhaust clearance. The reason I say both is because there are angles that would make this more efficient, less efficient, different things like that, but we do have the car in mind. We aren't designing this to cut up the chassis. This isn't a race car build. This is a street car build. So it's always both. We're always going to be a compromise between aero efficiency or exhaust. Usually we set it up with the factory exhaust with as much performance as we can get out of it, and then from there we allow the diffuser to adjust down for different exhausts, and that sometimes doesn't hurt performance, sometimes it does, and depending on how much you lower it, it'll kind of hurt the performance a little bit. And then another question was splitter tunnel options. Are we exploring to make more use of the dive planes? And that was also specifically on this car. As you can tell, there are no splitter tunnels on this car specifically. And the reason is because we don't think it's needed yet with our current wing. So this is the new wing that we're coming out with this car. It's also coming out on the BRZ. We just released a video on it. It's called the UCW. It's also coming out for the WRX. We consider it a medium range downforce wing. We think that's going to be good for the majority of people who are tracking this car. If we were going to put tunnels on it, we would either look at using the ones that we use for the Porsche, because those are a production unit, or something from like Professional Awesome. They have good ones also that are reasonably priced that we could apply onto the splitter. And we would need to run a bigger wing though. Basically our V1X is what we'd have to run to want to utilize tunnels based on what we feel the aero balance is going to be. Obviously with the virus going around, it's hard to get track time, but we're hoping to get the wing on our car fairly soon with the splitter and everything else. We currently have the dive planes and the diffuser. Once we have the splitter and the rear wing, we'll be able to get a better idea how it feels on track with the aero balance, and go about all of that. So that's kind of the questions from there. And then I'll kind of start going over some of the stuff for CFD Friday. One thing I'm going to pull up real quick that won't be on there. Let me find it real quick, and that'll kind of help with kind of answering what kind of plots we're looking at, because the plots are kind of the big thing. Let's see, let's open up this guy. So right now we're looking at just the surface plot on the car, and then we have a few different other plots that we can look at. So right now we're looking at the CP plot. I don't know why this isn't opening. Come on. I guess while I'm waiting for that to open, I will answer a few. Oh, there we go. Okay. So we have that. So basically this is so I can read some of the definitions. So we're looking at coefficient of pressure. This is in reference, it's actually like pressure. It's just a coefficient. So 0 is atmospheric pressure. And that's basically the easiest way to read it. So basically if you're looking at the image of this, blue is low pressure. Depending on where it's located on the car, it's either creating downforce or it's creating lift. On the bottom side, if you're looking at blue, it's creating downforce. Red is higher pressure than ambient, so it's going to either create lift if it's on the bottom side, or downforce so on the top side. Primary way to think of that is just looking at the wing. So the wing is blue on the other side. It's wanting to pull it down. Wing is also then red mostly on the top, which is wanting to push it down. That is the easiest way to think of that. There's also CPX and CPZ, which I output a lot of times for me to specifically look at. These are just a dimensionless number. It's so you can look at it in normal to either the x-axis, which will be drag. In our case of how we set it up, you can see the thing down here. X goes this way, Y goes this way, Z goes up. Those are standard coordinate systems for like airplanes and race cars. So if you're making negative force in the Z direction, that is down force. Positive force in the Z direction is lift. Positive force in the X direction is drag. Just so you have, so we're talking on the same thing. Another one would be wall shear stress. So this is, well, when it loads, this is a plot of wall shear stress. This is also viewed with, which is what's called LIC plot, which is a line integral convolution, which is used to basically visualize oil flow on the car. If you pay attention to any sort of engineering on Formula One, you'll see that they actually have some of this fluid. It's usually green, and you can see streaks in it, and you can see how the how the air is flowing all around the car. So that's in essence what we're looking at. This is a great plot for if you're doing some track testing. So we can specifically spray a section of the car and see if we are getting similar results on track that we are getting in CFD, to see if what we are actually testing is what's going on. That's mainly what we use this plot for. It's colored by wall shear stress, which is basically a force per unit area due to fluid friction on the wall of the car. This is basically used to visualize areas of separation and rapid changes. So rapid changes on the surface is going to be areas that you might have separation. So that's what that's used for in a simplified way. So you can kind of see how the hair is flowing. So you can see if I zoom in right up here, if it doesn't, some weird stuff. It's also very computer intensive to actually have these images, which is why I actually usually script them. But you can see how vortex is actually coming off here, and you can actually see it coming down the line along here. You can see there's some separation off the wheel well right here and down the side. And you can see basically how the air flowing around the Supra. Now another plot is, well, not another plot. We'll go back to CP real quick. I'll zoom out, and then we can kind of go over streamlines. So streamlines are great to show people kind of what's going on with the airflow. I don't use it a whole lot when I'm actually doing analysis testing and seeing what's going on. I feel there's better plots to use, but streamlines are good for the average person to kind of look to see what's going on. So you can see the airflow coming off the diffuser, going up and out from the wing. You can see what's going on right there. This is just streamlined down the center of the car. Pretty simple. It might even be offset. I don't know. Yeah, it's slightly offset from the center, but you can kind of see what's going on. I output a few different streamlines, so I don't know exactly. Okay, so this one's even more offset, and you can kind of see the airflow coming off over here. And then we have the last one is for the dive planes, so you can kind of see how the airflow goes off the dive planes. I think this will probably be the most useful one for people, so you can actually see how the airflow is attached. Hold on, let me drag it over so people on Facebook and Instagram can kind of see what's going on a little bit better. Sorry, it gets a little choppy from the moving it around, but you can see how the airflow actually fully stays attached up the dive plane as it goes up and around, which is pretty cool to see. So that is streamlines. Another one that we look at is cut plots. Cut plots I use quite a bit. I usually find those are more useful than streamlines. And usually how I look at cut plots is in terms of the total pressure coefficient, which you'll see as CPT usually. You'll see that if you can see on the screen, it's CPT right there. Anytime you see that, it's similar to CP. It's a dimensional number that's used to describe total energy of the airstream. It's mathematically it's the sum of the static pressure and dynamic pressure. And so in the red area, it's got all the energy. In the areas that's not red, it's been used up some energy. So there's some things, maybe we'll do a specific thing on cut plots on CPT one day, where you can kind of see more of what's going on and how we make decisions. But that's kind of the broad overview on that currently. This is a side view. Let me go normal to the actual side view so you can really see the stream. And then zoom in. Sorry, it's kind of big. This is why I have all my stuff scripted, so it doesn't take so long to do this. And there we go. Finding it. That's why I keep it all scripted. It makes this easier. Then I don't actually have to scroll through all of this stuff. I just have it automatically output images. So you can see this is basically the energy used up on the back side of the car. You can see how this is a good way to look. So people a lot of times ask us, how do you know where to put the rear wing, and how do you know how high it needs to be, or locations? And this would be a good point. The wing could actually go a little bit lower on the car based on this. However, that's not the full picture. Some of the other things on here that you would also want to look at is the interaction between the actual car. So if we actually lowered the wing, you would still have good airflow to it, but that low pressure region underneath there would interact with the car, which would lower the pressure on the top side of the car, which would actually create lift, and you would lose some of that low pressure on the bottoms of the wings, so you would actually lose downforce. So you would gain lift and lose downforce on that. So that's one thing you have to look at. Another thing you would have to look at is clean air. And you are getting plenty of clean air to the wing right here just looking at the CPT plot, because you can see it's all red. All the way around there you can see perfectly good airflow. Obviously a bad place if you're going to put a wing would be back in this area. That'd be terrible because you wouldn't get very good airflow at all. However, don't confuse that with necessarily for a diffuser, because what's going on underneath the car is a little bit different, and you can't look at CPT the same way, which is why I would do a totally different thing on just the underbody of the CPT plot. It's a good way to look at vortices and things like that. I do have another CPT plot. So this is a cut on the y-axis, so straight down the center of the car. The other one I have is just behind the rear wing, and when I'm talking about you can visualize vortices, that this will show how you can kind of see vortices. Let me do a close-up of that if I can move this how I want to. Okay, I need to zoom out. Apparently I don't remember these button clicks on here very well. Maybe it's shift, drag it. No, that's rotate. There we go. Okay, now moving it more to the center so we can focus on the rear wing. So this is where you can really start to visualize what's going on behind the car, and you can see how the vortice is coming off the end plate right here. So you can see it's coming around and curling right here. That's just a vortex coming off the end plate. That's why on the V1X we have slots on the end plates that decreases that vortex, which is actually there's a lot of benefits to that, and maybe I'll do a complete CFD Friday on that wing on a car. We put that wing on quite a bit of Porsches, so maybe I can do one specifically on a Porsche setup. You do lose a little bit of downforce with slots like that sometimes, not always, but sometimes. Usually when I say stuff, it's usually in aerodynamic terms, it's usually sometimes. There's always exceptions to the rules, and they're only soft rules. It doesn't mean that this is always what happens, but usually when you have slots on end plates, you lose a little bit of downforce, but you gain efficiency because you're cutting down on that vortex coming off the wing, which is causing drag. That's usually what those are for. Now in Formula 1, they got some fancy stuff going on that they do other stuff besides that, but in the generic terms, that's kind of what we're looking at. So these are kind of some of the images. I'm going to go over, I guess there are some questions that probably on YouTube that I will look at, and then also on the other ones. If you have the time to answer, would it be curious to see the effect of completely removing the side mirrors? Okay, we're actually going to be doing some tests with stuff like that in general. I can tell you usually the forces on side mirrors aren't super large. Obviously different cars, it affects it more. I usually do pull data from the mirrors actually, so I could pull that data up and look at some point and kind of give out generics. You can actually hand calculate a lot of times how much drag you're going to have on the mirrors too. If you open up a lot of books on fluid mechanics or even race car aerodynamics will have generic coefficient of drag shapes per shapes. A lot of times this would be seen as like a half circle, or there's things that are similar to it, and you can basically use the force equation with the coefficient of drag, which is just 1/2 rho v squared CDA. So you just have to know the area of it. So you could calculate the area of it pretty easily with just basic tape measure. You could use that shape. Rho is just density, and then you could calculate it at different velocities. Depending on what kind of, I would recommend just doing it in metric, as it's easier, because density and metric is a lot easier for the average person to understand than in English units, because it's slugs and stuff in English. It's weird. Instead of just otherwise it's 1.225 is what we usually use for density, which is standard density, and that's in, like, I believe kilograms per meter cubed, and then you just need to calculate your velocity in meters per second, and you can basically make a table in Excel pretty easily and kind of calculate and give generic differences of the mirrors. However, that's not going to totally change. That's not going to be 100% accurate because you are still going to have downstream and upstream effects from your mirrors being on there or off. So it will change other aspects of the car. But that'll give you a good idea how the forces act specifically on your mirror. It gives you a good hand calculation check, just for your information. Have you ran wind tunnel tests to verify baseline and finished design compared model versions? So yes, we have done wind tunnel tests mainly with our wing. We have a blog on that. Basically, it was to correlate our CFD work. We are also working on a project with another company with hopefully getting a scale model into the wind tunnel and testing a scaled model on a rolling road wind tunnel. And then we are also hopefully going to be going to a wind tunnel in the next few months. It would have been actually, I think, last week. Yeah, it would have been last week. But the virus kind of shut down a lot of things, so we have not been able to do that test, but we're hopefully looking at verifying our dual element rear wing changes on a specific application that we've CFD'd the whole car, and I believe it will be fully rolling road, and we'll get a lot of good data from that. And then there's another car that we helped design that will hopefully go to the tunnel also, that we'll be able to correlate a little bit with also. So yeah, we have done some baseline testing in the wind tunnel. We also have done correlation work with the drive air model and the Ahmed model with wind tunnel data. And we've done that correlation work. A lot of the correlation work is through scaled tunnel work too, which is interesting. So we scale the CFD model down. You basically go off Reynolds numbers and Reynolds scales and stuff like that. So we have done a lot of that work just to verify what we're doing is correct. I'm actually in the process of switching to a different open foam currently, and when I do that, I actually run the drive air model as a verification that any changes that they made in their code when I'm switching over to a new one, or any differences that are a little bit minor between the different releases, we're not affecting our results. So we use the drive air model a lot for not only correlation, but verifying that nothing majorly has changed in the code or our meshing is good. There's a lot of things we're doing besides that when we can't always get things in the wind tunnel because it is very expensive. Let's see, how would you set up boundary conditions on the front of the car? As is it stationary wall settings around the shell of the wheels? How do you come up with car geometry as a 3D scan? So I can actually show you how we do the actual car. I'll show you that in just a second. I'll just show you the files and you can kind of see what's going on. But for how we come up with the geometry, it's 3D scan. So this is a scan of our car that was then turned into CAD. So we scan the full car. We don't actually change it ourselves. We don't actually convert that ourselves to CAD because honestly it's a lot of work and there's very specialized people who do it, so we actually pay people to then convert that into CAD geometry, and then we make the changes that we need to it in CAD. We use NX for our CAD software, so that's how we do that. And then to get it into OpenFOAM, we actually output STLs. And then I output STLs per each individual file, run it through a script where it combines all the files into one object file that then has all the names of the patches in there. It's pretty handy, works really well. That's how we do that. Let me see, I'll kind of show you. So, where is OpenFOAM? OpenFOAM. So these are the different ones of OpenFOAM that I have that's running. So this is version 6, this is version 7, and this is version 1912. So this is the .com version, and both of these are the .org or Foundation version. So this was ran in version 6 of the Foundation version. So we are going into there, go into the file. We can go at, so this is where you set up your boundary conditions, at least in OpenFOAM. These are the file locations. So it's basically set up by what turbulence model you're using. Most likely you're asking about like the velocity stuff. So this is kind of where you can see what's going on the scripting side of things. So these are the wheels, rotation, the locations. So the vehicle is just set as a non-slip, and then the wheels are set as rotating wall velocities. This was not done using multiple reference frames, just because I don't always find that needed. Sometimes it is, and sometimes we'll run it, but it's not always needed. So that's kind of just how that's set up. So let me see here. What are some of the other questions? Do you have a cut plot for the GT86? Yeah, I do have CPT plots for the GT86, just not on the machine right now. We could probably do that. And then somebody with a funny name on here, would a more swoopy swan neck work better? I'm going to say that's probably Tom. Tom seems like that's a question he would ask. Because he's the one he's a friend of ours. He talks about swoopy swan necks a lot. So swan neck is better than bottom mount for efficiency, but it's also a lot more difficult to get good mounting solutions. So we will. So that's why on this wing we came up with a bottom mount solution, just because it simplifies things. It makes it easier to actually get mounting that's strong enough. With the problem with the swan neck wing is I can hopefully maybe show you a little bit on here why. Let me rotate. Let me just actually get this guy and the Y. Alright, so say we were going to mount this wing. Oh god, hold on. Oh man, zooming in. It's doing all kinds of weird stuff. Okay, zoom back out. Come on. Sorry, that's the problem with having big files opened. Why is this not zooming? Gotta wait for it to load. Okay, there we go. Super far back. Alright, resettled it, so hopefully it pulls it back forward sometime soon. So you can, there we go. Okay, so bottom mount. The load's coming on the wing right here. Look at my mouse. So if you're applying load, it's basically pushing down. You can assume it's pressing down in the location what's called the center of pressure, which I don't know exactly where it's located right now on here, but we'll just assume it's right here. So you would have a force pressing down right here. So all of that load is getting pushed straight down. So this whole mount right here is pushing down. And then you have drag, which is going to go in the X direction, which is one to pull it this way. So you're probably getting maybe a little upward pull here, but if you are, it's very minor, because you still are having a force being pushed down. And this wing's pretty efficient, so it makes more downforce than drag. So it's going to depend on the moments, but it's going to be pushing it down. The problem with the swan neck, though, is you're putting the mounts at top, and to actually have something that looks good, it's going to push the wing a little bit more rearward. So it's coming up like this and over. And so when the wing would actually be pushing down back here, which is going to want to pull up this front location. So that actually makes it a lot more difficult to design a swan neck style for mounting, that especially when it mounts to the trunk lid of a car. It just causes a lot of forces that are hard to counteract, which is why a bottom mount is a lot easier. Which is why when we were developing this wing, that was one of our primary goals. We wanted to be able to have a wing that we could actually mount to the trunk lid of cars properly and still be able to handle the downforce. So that's kind of the swan neck. But swan neck is more efficient. It puts the mounting onto the top of the wing. The top of the wing doesn't produce as much downforce as the bottom side of the wing. The bottom side of the wing is the one that's doing the majority of the work. So you want the cleaner airflow to it, which is why swan necks are usually more efficient than a bottom mount wing. Hopefully that answers that question. Are there any industry standard approaches to your solution? For example, when you do a structural in New York City, you need to follow building codes with giving load. I wouldn't say there's a standard exactly like that. There are best practices, I would say, that we do follow. Majority of best practices. The thing with automotive and motorsports is a lot of best practices are kind of kept inward. A lot of people don't. Yeah, they're trade secrets. They don't tell you exactly what they're doing to get the results. We've done as much work as we can to make sure what we're doing as proper as we can, and we try to tell people the assumptions we are making, so you can make a decision yourself if you feel the numbers are accurate or not, for you. I wouldn't say that if we say it's making 500 pounds downforce, I wouldn't say that you're going to be able to go on track and say it's making exactly 500 pounds downforce. It's going to be making around 500 pounds of downforce. And it basically, we look at trends. So is it making more downforce, yes or no? And can we trust those trends, the trends to be accurate, not the actual raw number that's coming off. That's usually why we don't post raw downforce numbers. We post deltas from stock to this, because the delta is much more accurate than the raw number. Hopefully that kind of clears things and makes more sense. But there's no, there probably is more of an industrial standard approach when you're talking about aerospace. I'm not in aerospace, so I don't know. I know CFD is handled a little bit differently there. I know there's a lot more of a standard on meshing of airplanes than there is on automotive cases. Just talking with people who do industrial meshing on automotive and aerospace. Aerospace is a lot more critical on their meshes because drag is a lot more sensitive. Their meshes are a lot more exact, and their geometry is a lot more simple too, so it makes that easier. A lot of automotive geometry makes it very, very difficult to get the kind of boundary layer growth that aerospace uses. So that's kind of a little bit of the difference. That's actually an interesting thing I've talked to some aerospace guys about, and it's really interesting to hear their takes on CFD versus like automotive side of things. So that's those questions. I'm assuming there are some questions on here. Let's see here. What other questions? They said, hope we're staying safe and healthy. We are. Things are pretty good here. When are we getting the GVA diffusers? That's a good question. I don't actually know. Did we order those, or have we ordered those? Are we going to order those? Wait on. I don't know. Clay, what's a GVA? Which car is that again?
I don't know what a GVA is. I know GV is the one we have, sedan.
Did we order diffusers? No.
No.
Okay, well, we have prototypes, but we don't actually have diffuser. Or we have our prototype.
We're looking for people interested.
We're looking for people who are interested in it so we can actually order production.
Yeah, we're doing a group buy. Email us.
So we're doing a group buy. So if you're interested, email sales@varus-engineering.com, and Clay will handle that and get you on the list and stuff like that. It's designed. It's been tested. We have the whole GV car. We have a lot of stuff actually designed for the GV car. We just haven't had as much interest, so we haven't gone to production. So, this is. So I'm learning AutoCAD CFD. What program you guys recommend me to learn that is mostly used in the industry? I would say it depends on what industry you want to get into. Different industries use different things. If you're looking at automotive, the big three CFD softwares for automotive is OpenFoam, which is what we're using, ANSYS Fluent, which is what we've used in the past, and Siemens Star CCM. All three of those are fairly industry standard. Any of those you use, like if you know how to use those, you'll probably be able to move on to other things. I would say with fairly high confidence that OpenFoam is the most difficult to use. So if you know how to use OpenFoam, you will be able to move on to Star CCM or Fluent without any problems. The easiest to learn would probably be Star CCM. However, I know Fluent's been making big strides in making their software easier to use, but Star CCM has a pretty good user interface and is pretty clean and easy to use if you're just getting into it. So however, those two are expensive. OpenFoam is free and open source, so there's that. That's one reason we use it. Let's see, any other questions on here? Is that a moose around your walls? I don't know what you're talking about with the moose around your walls. Oh, mouse. Is that a mouse around your walls? If you can clarify that, I will be happy to answer. There's someone behind the wall. Okay. Gotcha. There's somebody behind the screen. Gotcha. I think they're talking about your girlfriend. I think they're talking about because that's from earlier. Have you looked into the effect of how it would be if you blocked off the... Have you looked... Oh, this is Tom. Have you looked into how effective it would be to use the blocked off vents on the Supra? Oh, yeah. Eric did a big rant on this thing. The vents aren't useful at all. Like, even if we made them use... It'd be, like... I'm not saying that if we opened it up and tried to go about it, we couldn't make them useful and do something, but it would require a crap ton of work to make anything useful.
Well, show them that the top one's like a pile of garbage.
Oh, well, yeah.
It's like high pressure.
Yeah.
That one's high pressure.
Yeah. It's definitely not the lowest pressure behind it. Like, right there is definitely not good. You might get
Maybe
some
with
stuff
wipers.
coming out here. Yeah, you could probably make them work. I don't know. It's not... The door one, I don't know what they're doing with that. That's just like a big open cavity. Like, that's what you would have... like on a Porsche or something, and you have like an engine intake there or something. But actually, dude is asking if we have a dealer in Korea. We do have a dealer in Korea. Clay, what's our Korean dealer?
M7 Industries.
M7 Industries is our Korean dealer. Clay is pretty good friends with the guys over there. They just did a pretty cool video on some of our Miata parts. So I would hit them up if you are looking for that kind of stuff. When will you guys have the 2020 A90 Supra rear diffuser? We do have prototypes of it, but those are all gone. We have one on our car. We are looking at 6 to 8 weeks till those are done. It is a somewhat of a process to get that all done because they go through a few different steps between cutting the sheet metal, bending the sheet metal, riveting the sheet metal, because our production units are all hard riveted, which is super cool, powder coated, and then they get silk screened. So we're hoping that industry in the United States starts coming back a little bit more and things don't slow down more, so it can all get done. They are all made stateside through a few different processes, so hopefully sometime soon they will be ready. Clay said 6 to 8 weeks, which is probably fairly accurate. Let's see, that side port could possibly be adapted for rear brake cooling. Maybe. The problem with the rear brake cooling is it actually is part of the door, and you'd actually have to cut through the door and then the rear quarter to make it possible. So since it's connected to the door, that's why I think it's a weird setup. So it's very odd. Any side skirts going to be made? We are looking at doing side skirts. We have not designed side skirts yet or done any development work on side skirts. So hopefully sometime soon. The Supra seems like a fairly popular platform right now. So because it's popular, we will probably look into doing more parts for it. We just haven't. We need to finish up the wing, which we have some cool parts coming off the mill for that for prototypes. So we're pretty excited for that. Eric knocked it out of the park with the machining on them. They look awesome. He's also the one that helped with the sweet design on the uprights. We're a big fan of the way the uprights look and are designed. So the wing's going to be hopefully soon. The splitter is also hopefully soon. We have production coming for the dive plane, so those will be the next big release. Will be the dive plane and then the rear diffuser, obviously. Then we need to get the splitter out and the rear wing, and once we have those, we will be looking at other parts for the car. So if you have things that you specifically want for the car, please email us, because we would love to know what you actually want to see for the car in terms of development and products, because we are happy to make them and design them. All right, so that is all the questions on Facebook. Now let's go, or maybe Instagram. I don't know which one I was just reading off. Now I got to this other one. Oh god. Oh crap, I'm moving around this stuff. Let's see. Oh, we got a lot of stuff. Let's see. Alright, I'm not going all the way up because there's a lot of questions on, or there's just a lot of people who've come in and out, so somebody wants more products for the ST, which we might do. You never know. We're looking at splitters and stuff for all kinds of stuff, so we might do that. Do you guys do tunnel baselines to correlate your model? Like, I went over that earlier, so I won't go over that again. Let's see. How do you go about optimizing aero around the tires? So that's a kind of a tricky thing. Usually usually we just deal with the tires more than anything. We usually optimize for downforce more so than drag, and tires are a big drag issue more than anything, but it is less of a problem on a fendered car than, say, an open wheel car. They're much more detrimental on a open wheel car, so it's less of an issue. We try to just avoid them with air is the main thing that we do. We make some parts that are for that, but not a whole lot. Let's see here. Alright, make me want to buy a Supra to have your products. Appreciate that. What kind of power returns are you expecting? I'm assuming you mean downforce, and I'll bring up the data for that in just a second so you can actually see the data. Less downforce, okay. The amount of trunk space in that corner is none, yeah. Instagram view is much better than Facebook. You can thank Eric for that. He's the one who set that up. Let's see. Do you have a dealer in South Korea? Yeah, I just mentioned that a little bit ago. I am from Tajikistan. I'm sorry, I can't pronounce it, but welcome. I'm glad you're watching. What about the Infiniti G37? I don't know if we will actually do that, but maybe we'll look into it. Then will you be making suspension components for the Supra? Interestingly enough, we have some on the table just behind the screen that we are working on prototypes. So that is Tom probably. So Tom can message us and find out exactly what that is. Openfoam.com or .org. This is currently done on .org, but I am in the process of switching to .com. Bruce is the one from M7, right? Dozy.
But Bruce is one of my really good friends.
Okay, well, Bruce said hi. So,
Bruce?
Clay's right over here, so. Alright, so. Okay, so, perfect. Let's see, I think there's a few more questions now on YouTube, and then we'll be ending it for CFD Friday since we've been almost going on for about an hour, so. Let's see here. Makes sense. Have you or will you show your mesh? This is more of a trade secret. Interesting to know how you spread your mesh out and along the car to save resource count. That's a good question. On here, I am not going to show it, but I can do a specific one where we do show kind of it that doesn't give away too much of like what we do. I'm not going to show our snappy code or anything like that just because I feel like that gives away too much, but I don't have a problem doing some cut planes on a future one and kind of go over, maybe I'll go over meshing in OpenFoam or something. A lot of people think it's more difficult than it really is and don't think you can get a good mesh in Snappy, which I disagree with. I think you can get really good meshes. It does have a weakness in layering, but there are some cool tricks around that, and I think that you can get some pretty good stuff. So we are PC. We are not cloud, but we have the ability to run on a cloud. What's really nice about OpenFoam running on the cloud is it's basically just like a bunch of text files in general. So you can easily upload like the text files for your cases, and a lot of what we're running is very similar. So you just edit text files. So the only thing I would actually need to upload from the cloud is the actual CAD file, and then I can just download our text files that I run through Python for getting our data and images. So basically I would only need to upload, I don't know, a few hundred megabytes of CAD data, and I can download a few hundred megabytes of actual raw data back. I don't have to be uploading gigabytes of stuff. Like if I were to set up something in like say Fluent or something like that, you'd have a much bigger case to upload up into there to actually run on the cloud. So that is a huge benefit with using OpenFoam on cloud-based. We have looked at running cloud-based on some stuff. That's probably what we're going to go with when we're running like DES cases, just because running that on our system takes like a week, and it's just not useful. So overall, but there are some cases where it is useful, and we'll probably end up running those on the cloud instead and getting more computing power in. let's see. Have you gone over? So we are running basically 20 core CPU, 210 cores, and 256 gigabytes of RAM. Would you recommend Ryzen 3900X or dual channel or Ryzen with a quad channel? Honestly, I don't know enough about the Ryzens. If you have the budget, I would go towards the Rome EPYCs, the Epics. Those look fantastic in all the benchmarking. That is what we want to end up moving towards, is the Rome version of the Epics or whatever they come out with after that. They are very fast. Just looking at it, I would lean towards the quad channel Ryzen over the dual channel, just because I know RAM throughput of getting stuff through is one of the big holdups on CFD. So I would lean towards quad channel, but I'm not positive. I don't know what software you're specifically using, but if you look on, you can go to CFD Online, and they have a lot of, in the hardware section, they have a lot of different things for benchmarking that you can, I'm sure somebody's ran something like that, and there's some really smart dudes on there with computers that can help answer questions with that too. That's who I would lean towards, just because that is where I am not an expert by any means. I just know as much as what I read. So, that's everything. I'm going to close everything down, and hope everybody enjoyed the CFD Friday. We'll try to keep it going and keep doing it. So if you have any questions, email us, sales@veris-engineering.com. If you have any future questions or something specifically you want us to look at, and we can go over all that at a future date. Thank you, and bye.